So, first thing I want to do is I want to take you back to for like a whirlwind tour of parametric equations, which you spent time doing last year, and I sort of want to refresh your memory about what you did, and then show you some new things, like, hey, this is how we might apply calculus to that. And I'm going to do the same thing tomorrow with parametric equations a little more. We're going to talk about arc length tomorrow. So, first things first, we can take a look at like that first one. Where x is, what is it, root t, and y is 1 minus t. Did I get that right? Okay, so here's the thing. We've been taught for many, many years now that like y depends on x. And that's fine, but there are times and there are ways of looking at x and y where they don't depend on each other, but where they depend on a third independent variable like t. So here, x and y are both dependent variables. They depend on what t is. And for my physics friends, you can imagine this like when you're taking the components, right, of like, position or something. You know how your x component of position depends on velocity and time, and you know how your y component of position depends on velocity, time, and 1/2 g squared, right? Right. So they are both functions of time, and we've actually seen this in this class too. Like when we do related rates, x and y can be functions of something else. So here it is, and the idea is, hey, if you tell me a t value, the independent variable, I'll tell you a coordinate, x and y, and the dependent values. And maybe actually getting our calculators out, or you can just watch, but your calculator does this, and we can show you how the table will work, and what the graph might look like. So your calculator has a parametric mode. Nice. All right, so first things first, if you want to use your calculator to do parametric mode, you need to go down to function, parametric, polar, sequential. Those are all the different modes that your calculator has, and you want to select parametric. And when you select parametric, you just arrow over to it and hit enter, and now you are in parametric mode. Once you're in parametric mode, there are a few things that change on your calculator. So like when you go to y equals, all of a sudden, you have x1 of t, y1 of t, x2 of t, y2 of t. You now have pairs of dependent variables, x and y, that depend on t. And if you do like square root, and then you press like the x button, you get a t out. Right? Because your calculator, when you're in parametric mode, now knows that t is the independent variable. So I can actually graph this function. And before I even graph it, let's just play the game like, hey, pick a value for t, preferably one that will be easy to do. Pick a value for t, and we'll see what the coordinate is. Pick a value.
9.
All right, 9. If I pick 9 as a value for t, my x-coordinate is 3, and my y-coordinate is 1 minus 9, which should be negative 8. So I get 3, negative 8. And it's important to understand in this case, when we're talking about square root, we're talking about principal square root, the positive square root. We can't have two outputs for x here. Okay, so I know that 3, negative 9 is going to be a point on my graph, and as a matter of fact, 3, negative 9, 3, negative 8. So if I go down on my table, if I do second table, you can see that when Emily picks 9, the x value is 3, the y value is negative 8. Now look, when you graph a parametric function, you don't actually see the t value. All you see are the x and y coordinates. So the t value is sort of like an invisible variable, but it's an important variable because x and y depend on it. Okay? Is that okay? And if we picked 4, we'd get 2, negative 3. Does that make sense? All right, so before we graph it, I'm just going to show you when you go to your window now. When you go to your window, you actually get not just x min, x max, y min, y max, but you now get this t min, t max. So it's like saying, hey, if you want me to plug in values for t, can you give me an idea of which ones you want me to plug in? So I know that I'm dealing with the square root of t, so t's got to be positive, right? All right, so t min's going to be 0. And then I don't know, what do you want t max to be? It doesn't...
You get 36.
All right, so 36 is going to be pretty big. I'll do it.
I like it. 25.
I'd even say 25 is a little big.
10. 16. 9.
Like I'll do like 9 or 16. I think would be good, and I'll show you why in like 10 seconds. So if I pick 16, the next thing we want to ask is what the t step is, and that means how often do you want me to plug in t values? Now, if you have t step as 1, basically from 0 to 16, what's that? 17 values, including 0 and 16. So you're only going to get 17 points on the graph. And if you remember like the Euler method, like you're basically taking, it's going to be sort of chunky. Like you're only like stopping every step, or you're only stopping every step. So it's like not going to be a very fine graph. It's going to be coarse.
Those are exact points though.
So it's right. It's not like Euler's in that we're approximating. You're absolutely right. We get exact points, but it just, the way your calculator works, it connects the dots, so it's going to look sort of like a connected dot. So if you do a t-step of like 0.5 or 0.1, it connects more points, and that's why if we were doing 36 and I had 0.1, that would be like 360 points your calculator would graph, and it would actually take your calculator a little while to do that. So I'll stick with 0.1 and see what happens. And if we don't get enough of the graph, we can always go back and change. I have my x-min -5 to 5, my y-min -5 to y-max to 5. If those didn't work, like I'll go back and change them. All right. So when I go to my graph, I get something that sort of looks like that. You can see the calculator is actually really plotting those points. And gosh, we had it go all the way out to t equals 16, which would be x equals 4. Oh no, that was good. That was really good. That worked out well. Okay. So we get something that looks like that. What's it looking like, if you had to guess?
Negative x squared, but the absolute value. Well, like, maybe we can say something to a negative fraction.
All right, so
like x to the -1/2. Maybe.
So I like this negative x squared part, but I hear what you're saying. You're saying we're not getting the whole graph, and I think what I'd say is this. What kind of values for t do I have to plug in?
Whole or squares to get like.
I don't have to put in squares, but what do I have to put in?
Positive.
Positive. If I plug in positive values for t, what kind of values am I going to get out for x? Positive. So I want to put this on the back burner for us to think about when we do this a little bit more with this same function. My domain for t is t has to be greater than or equal to 0, which means my range for x is going to be x is greater than or equal to 0. That's going to come into play in just a little bit when we eliminate the parameter. Okay, and that's what I think you remember doing from last year. Greg, and then let's eliminate the parameter.
Like, if we have square roots, would there be some point where we do like non-real numbers, so like I?
Ooh, I got excited there. I dropped the pen. Okay, so here's what you're going to do. You're going to take 3 semesters of college calculus, of which you might place out of 1 or 2, and then you'll take like multivariable calculus. Then after that, there are a couple courses of action. There's real analysis, which basically goes back and proves everything you've learned in calculus. So it's a mathematician's course. It's like, hey, we are doing proofs. So everything that I sort of like said, hey, here's a picture, or do you believe me, or I'll do a little bit of algebra, like they'd go back and like rigorously prove everything.
You can't see. I don't know.
Seems like
There's
close the door.
Then after real analysis, there's complex analysis, which says let's go back and do calculus all with imaginary numbers now. So yeah, I guess you could say you might not feel it right now, but we're starting off easy so you can do more complicated things later. We're not doing that right now, though. Okay. So I think last year in pre-calc you worked on eliminating the parameter. I want to tell you this. We're going to do that, but I want to convince you that you don't always have to eliminate the parameter. Like, that's actually not the goal of parametric equations, because if you can eliminate the parameter, then there's not much. Something. Then there's not much reason to use parametric equations, right? The idea behind parametric equations is it lets us represent points in the coordinate in a way that we might not be able to otherwise. Now this one we actually can express it in both ways, and so let's see. Is that t equals x squared? And now I'd get y equals 1 minus x squared. Or negative x squared plus 1. But I'm going to remind you, we just talked about, right? T has to be greater than or equal to 0, which means x is greater than or equal to 0. So this function is appropriate so long as x is greater than or equal to 0. And that's why we only get half the parabola. All right, questions, comments, concerns?
So that domain, x is greater than or equal to 0, that comes from the equation right there where we say t equals x squared.
It actually comes from here, right? So I would say, here's the thought process.
Solving for t.
T, the domain for t is greater than or equal to 0, which means the range, right? X depends on t, so the range for x is greater than or equal to 0. But now, if we want to eliminate the parameter, x now becomes the domain. So what was a range in this function now becomes the domain in this function. Okay. Did you do a lot of this with Mr. Wotus? Yeah. Okay. The other class was telling me something about like overlapping domains and ranges or something, and I have to be honest, I don't remember doing that.
I do.
Well, good. We're all even then.
I remember doing it actually, but I don't remember how to do it.
Okay. I don't remember doing it, so I'd have to go back and look at what it is you're exactly doing. But nonetheless, I just want you to be thoughtful about what it means in parametric mode, what sort of domains and ranges might come out. I don't know about this overlapping thing. So I want to take a brief aside to talk about like parametric functions with trig functions, and then come back to this problem. But anything about that? Does that feel like familiar, even if you didn't remember exactly how to do it before? Like, Julian, oh my goodness.
Sorry.
All right. So if we look at B, I think that's, what's that? X equals, is it 1/2 cosine theta?
Yeah.
1/2 cosine theta and y equals 2 sine theta. So I just want to remind you, more than anything, that when you have trig functions, sometimes you need to exploit like little tricks. And to me, when I see a sine and cosine, do you recall any relationships between like?
Oh.
Say it again, I'm proud.
Cosine squared plus sine squared.
Right. So I'm going to actually exploit that by rewriting this as 2x equals cosine theta. Did I do that right?
Yeah.
And 1/2 y equals sine theta. And now that I know what cosine theta and sine theta are, I can use exactly that Pythagorean identity that Emily said. If I say, hey, sine squared theta plus cosine squared theta equals 1, well, what is sine squared of theta in terms of y?
1/2 y
1
squared.
y squared.
1/2 quantity y squared, which would be 1/4 y squared
Looks
plus
familiar.
Plus 4x.
4x squared equals 1. And to me, that's like, it's almost like a circle, which means to me that it's actually an ellipse, right? Because my x and y scales are different. If it was like x squared plus y squared equals something, it would be a circle. This is like, I'm pulling the x, I'm like stretching x in one direction, I'm stretching y, and isn't this like, what, a major axis of like 2? Isn't it
I
over
don't
b,
remember the ellipse rules, but
over
yeah.
b squared? And this would be x squared over 1/4, so this would have like a minor axis of 1/2, right? Yeah, I'm not remembering totally either.
Yeah.
So if you came back to me and said I was totally wrong, I'd believe you, but that's sort of what I'm remembering.
Are we going to go deeper into conic sections again?
We're not going to do like a ton with conics.
Okay, that's really.
No.
Except for Ben.
No. Oh, if you mean good, like you mastered them and it would be boring, that's fine.
That's what I meant.
If you mean like good, like you never felt good with them, we should talk about them at some
Yeah.
point. Probably not today, maybe not even in class, but I want you to like I would like it if you walked across the Shipley stage. You have a few more years. If you walked across the Shipley stage saying like, yeah, I could do conics. Right? Okay. So is that okay just as a trigonometry aside?
Yeah.
All right. I want to come back here. And now I want to talk about the derivative of a parametric equation. Now, obviously, you could tell me that the derivative of this is...
Negative 2x squared plus x.
Mm.
No, plus 0.
Negative 2x.
Negative 2x
2x
plus 0.
Right.
You know.
Yeah. Well, it's hard. You know why? Because we're switching gears and talking about derivatives, and we've been spending so much time talking about antiderivatives. Okay, so we're switching gears a little bit. So I want to show you how that relates, but I also want to remind you that parametric equations are often used for functions that can't be written as y of x functions, right? So we can't always eliminate the parameter. It just so happens in pre-calc we give you lots of practice eliminating the parameter, but it doesn't always work out that you can do that. So I'm going to go to my graph, and I'm going to trace my graph. And I want you to notice that as t goes up by 0.1, what happens to the y value?
It's decreasing by 0.1.
Okay, it's decreasing by 0.1. Awesome. As t goes up by 0.1, what's happening to the x value? Is it going up by
No.
something?
It's going up by the square root of 0.1, isn't
It's going up by something, but it's definitely not 0.1, right? Okay. So this might not be earth-shattering, but if you have a parametric equation and you want to know what the derivative is, it's the derivative of y with respect to t over the derivative of x with respect to t. In other words, y is changing at some rate with respect to t, and x is changing at a different rate with respect to t. If you want to know how y and x change with respect to each other, just take those ratios. As a matter of fact, can you almost imagine just dividing the numerator and denominator by dt to get this? Or multiplying by dt over dt to clear fractions and get this? Like, it sort of looks like it should make sense, right? So there it is. That's the derivative of a parametric equation. And if we were to take the example we just had, let me try again. X equals root t, y equals 1 minus t. If we were to take this example, all it says is if you want the rate of change of y with respect to x, just differentiate y with respect to t. So it's the derivative of y with respect to t. Say it loud and proud. -1. And now differentiate x with respect to t.
it? Negative 1 over 2 root
1/2 t to the negative 1/2.
And we might not write it that way, right? We might actually write it as -2 root t. Did I do that right?
Oh, yeah.
You can tell me I did it wrong. If
No,
my
you're right,
algebra
you're
is
right.
suspect, you can let me know.
I think it's right.
It's right.
Now, I want to point out something. This derivative is in terms of t. And if you're in a parametric situation, that makes sense. It should depend on t. X and y depend on t, so the derivative of y with respect to x should depend on t. But if it makes you feel better, what's root t equal to?
X.
X. So if you wanted this one, in terms of x, you could say, hey, the derivative is -2x. Well, that makes sense, because remember when we eliminated the parameter, the function was y equals 1 minus x squared. So doesn't it make sense that the derivative in terms of x is -2x? It does. Okay. It's a good place to pause for a second. Questions, comments, concerns? Your calculator does this. Now look, your calculator will not tell you that the derivative of y with respect to x is a function, but if you wanted to, you can go to second calc, and because we're in, what does it think my finger is? It thinks my finger is an eraser. Let's change that. You can go to second calc, and notice that you can find the rate of change of y with respect to x, the rate of change of y with respect to t, the rate of change of x with respect to t. So if you go to 2, dy dt, and let's just take like 1 as an example, the derivative is negative 2. And that should make perfect sense based on the information we just did. We just said, hey, it's equal to negative 2 root t. It is. When t is 1, the derivative is negative 2. All right? I know.
Not
And it's
this.
all right.
Not this.
All right, so
No.
the next part is going to be a little confusing. Okay, so I want to talk to you about the second derivative. I actually have written myself a few notes to make sure I try to make it as less confusing as possible. It does just come down to memorizing a formula, but I'm hoping that I can get you to see why the formula works, so it's not just memorizing, but it's understanding a formula. So I want to say, if we're talking about the derivative of a parametric equation, it probably makes sense to also talk about the second derivative, right? Concavity, right? This would tell us about increasing and decreasing. Well, we might also want to talk about concavity. So let's see. We found here that this was negative 1, right? And dx over dt was, what'd you tell me it was? 1/2 t to the negative 1/2.
Yeah.
All right, so I'm just going to keep that in the back of my mind. Okay. So. So far, so good. Now, I could write that like this. They mean the same thing. Because that's what this is a operator. The derivative of what with respect to x? The derivative of smiley face. So I can either put the smiley face up by the d or I can bring it out front. And if this were the question in parametric mode, I would say, oh, that's right. All I'm doing is rewriting this thing over and over again. So far, I haven't done anything really earth-shattering. Is it okay?
So
Hold on. Sorry. I know I said is it okay, and I didn't really mean it. I might also write it like this. All right, go ahead now.
So how are these two, the smiley face equation and the left-hand equation, related?
They are the same equation.
We're just replacing y with a smiley face?
Exactly. So there's nothing earth-shattering other than I'm using it to set up what I'm about to do, which is going to look confusing, but can be considered less confusing if you think about the smiley face. Okay. So if you've been writing down, you really don't have to. If you want to, that's fine. You can continue doing it. But we're going to get to what I want to show you in a brief moment. So we ready? Okay. I'm a little nervous. So if we want to take the second derivative, now we write it that way because it's really that's why the notation is like that. That's why the 2's are where they are. The derivative of the derivative, well, this is the operator for derivative, right? So we're really saying the derivative of y with respect to x, now take the derivative of that with respect to x. And we write it as d squared y. And if we really wanted to be clear, we'd probably put a parentheses around the dx squared, because that's what it is. That's how we write it. And that's why the notation has the 2 after the d and the 2 after the x. It's meant to be that way. All right, you ready?
Maybe.
I feel like I might be like blowing this out of proportion, but that's okay. All right, so I just took this and moved it up to the numerator. Okay. And now, here's the thing. You know that if I have the derivative of a smiley face with respect to x, if I want to write that as a parametric, all I do is say, hey, it's the derivative of smiley face with respect to t over the derivative of x with respect to t. So I'm just going to write the derivative of smiley face, which in this case is with respect to t over the derivative of x with respect to t. And an equivalent way of writing that is and what I'd like to do really is I'd like to show you how we would take the second derivative of the function that we just did. I'd like to tell you why some students find this a little confusing and then do any questions. Okay?
Is that the end result?
That's it. Okay, that's it. So if you wanted me to, whoops, let's not do that. I might say, hey, oh boy. All right, we didn't really need that anyhow. Oh wait.
And that's how you write the second derivative for parametric.
Yeah,
I'm
hold
just
on.
confused. What
Even
exactly
though
are we saying the derivative of t? That's
Hold on. I told you what I want to do, right? So what I want to do, I want to take this and I want to use the example. I want to tell you why students might find it a little confusing. Whoops. All right, so come on. So that's like the second derivative. So that's like, so if we take the equation that we just had, and we said, hey, we know that x is equal to root t, y is equal to 1 minus t. If you want to find the second derivative, the first thing you have to do is find the first derivative. All right, well, we did that, didn't we? dy dx is dy over dt over dx over dt. So what's the first derivative? Do you remember what we got?
1, 2, oh, you mean,
Negative 2 root t. Is that it?
yeah.
Okay. So I have found the first derivative. And as a reminder, it came from the fact that, hey, the derivative of x with respect to t is 1/2 t to the negative 1/2. The derivative of y with respect to t is negative 1. Okay? So now it's just a matter of like figuring out what we did and what we need to do and plugging in. So if I want to find the second derivative for this example, take the derivative with respect to t of the derivative. So this is the derivative. So I need to take the derivative with respect to t of negative 2 minus, well, negative 2 root t. What's the derivative of that?
negative,
One
or no,
x.
negative
No,
t to the negative 1/2.
Negative 1 over root 2.
So exponent's 1/2, so it's negative 1 t to the negative 1/2. And can I leave it like that for now? We can switch it in a second, but right now, all of that over dx over dt. Well, I already found what dx over dt is. Whoops. Actually, dx over dt is right there.
it's just
So it's 1/2 t to the negative 1/2. And let's see, maybe just to make sure we understand the derivative of that is there, and that's how we got the t, right? Hey, you know what that's equal to?
-2.
It's equal to -2, which makes perfect sense because remember what we said, the original function, if we eliminated the parameter, it was 1 minus x squared. Y prime is -2x. The second derivative is -2. So it all makes sense that that works out that way. So I'm going to pause. We see how it works. Students are confused because oftentimes they think they need to take the second derivative or the derivative of the derivative in the top and the derivative of the derivative in the bottom. Or they don't take the derivative of x with respect to t in the denominator. So this is really important, figuring out what goes where. Go ahead.
So, I understand what we got on the bottom. That's simple. That's dx over dt.
Okay.
On the top, we have dy over dx.
Which we found before, right? We found that
It was
dy over dx is
right.
-2.
So where did it go? How is it?
So I have to take the derivative of that. So what's the derivative of yellow with respect to t, right? Or green? Is that green? That's a neon green. That's or I don't know what it is. All right.
Yes.
So it actually behooves us to make sure we have the derivative of y with respect to x in terms of t. And then when we take the derivative of that again with respect to t in the numerator, we just need to remember we also have to have dx over dt in the denominator. So it's a little confusing. It's not that it's hard to do. It's just a little confusing.
So weird that math works like this because it seems like it'd be a joke if you actually if they should work out, but it does. It's
And here's the other thing, and I want to like
the
Alina-
method is so simple, like and straightforward, and it actually works.
it does, and the thing is, we probably would never use parametric equations with an equation that we could solve in terms of like functions. So it's nice to see that it works out, and it's convincing. It leaves us thinking like, oh, that works, and that's nice. But oftentimes it's going to be you're working with parametric equations that you can't get into function form, and that's why it's important to be able to do this, because you can't always go back to function form. Okay?
A lot of errors that may be made.
Algebraic,
Yeah,
right?
Algebraic.
Yeah,
no.
right. Plugging in and maybe organizational, just right, knowing what to plug in and taking it step by step. So tomorrow we'll come back and we'll look at arc length. I think arc length is actually a little bit easier. I think the first derivative in parametrics, pretty straightforward. The second derivative, you just have to like stay the course. All right, let's see. Oh no. Shoot. I don't know. I think it didn't let me do a new one. I'm not quite sure. Oh, no, maybe I'm wrong. Window. Oh, good. Does it think my finger is something? I think that my finger is.